All right, let's talk a little bit today about electron configuration. Hopefully this is a review for you from regular chemistry, but I just want to highlight a few things here. First of all, if you're trying to remember what the heck electron configuration is, just a quick reminder: 1s2, 2s2, 2p6, dot dot dot. Okay. So when we talk about electron configuration, that is what we are referring to. Let's talk about where all that stuff came from to make sure we all understand that. First of all, on the periodic table, the electrons in the atoms are organized by what are called shells, or we also call them energy levels. So if you think about a periodic table, looks more like this. The energy level, or the shell, is the number on the side here. So 1, 2, 3, 4, 5, 6, 7 are the shells or the energy levels. So that's like the big part. And then within each shell or each energy level, there is one or more subshells or sublevels. And within those subshells or sublevels, there are things called orbitals. Okay, and we're going to talk about all three of those. And basically, the electron configuration, this thing right here, is written based off of the number of electrons in each shell, in each subshell, and in each orbital. Okay, the subshells, remember the second one here, the subshells or sublevels are not the numbers on the side. Remember the numbers on the side here, those are the shells. The subshells are the S, the P, the D, and then down here at the bottom are the F subshells. Okay, so it goes S, P, D, and F. Okay, and each of these subshells is also divided into what are called orbitals. Again, we'll talk about orbitals here later on. Okay, and here's what we do here. So to determine the electron configuration of any element, so for any element on the periodic table, if we're trying to write the electron configuration, first of all, we have to follow what's called the Aufbau principle. And the Aufbau principle means you have to start at the lowest energy level or the lowest shell, which is the very first shell right here. You always start at the lowest shell first and then fill them up. And until one's full, you keep adding to that shell and subshell. Once it's full, then you keep going. So to do this, the first thing is you use the period number. Remember, the period number is that number here on the side, the 1, 2, 3, 4, 5, 6, 7. The period number shows you the shell number other than the D shells. We'll talk about that here in just a minute. So for example, here when I said 1s2, that 1 was referring to the first shell. The 2 was the second shell. That 2 was also the second shell, etc. Okay, the block shows the type of the subshell. So the block is the S, the P, the D, or the F. So notice I didn't just say 1, I said 1s. And then I did 2s and then 2p. And then for number 3 here, you add 1 electron for each element until that subshell is full, and then you go to the next subshell, etc. So to me, the easiest way to do this is to just do it. Okay, so selenium. So first of all, we have to figure out how many electrons does selenium have. So we are going to come back here. We're going to go to the periodic table. I think this is actually for regular chemistry, but it'll work just fine here in Canvas. So selenium, oh, that's great, error. All right, let's go to AP here, and we'll take a look at that one and see if we can get the periodic table off of that. Unless, of course, Canvas is down or just moving horribly slow. Looks like it's just moving really slow at the moment. So we'll go to AP Chemistry here, if it'll pop up. There it is. And AP Chemistry, hopefully we will have that periodic table in there that we can look at. There it is right there. Let's see if we can actually see it. If not, we can download it. It looks like it's going to pop up here. And maybe there it is. So we're going to try to rotate that to the right. All right, so selenium over here, right here, is number 34. So let's kind of go through this part here together. So it has 34 electrons. So again, always start there at the top of the periodic table. Always start with 1s. That's the first energy level, and that's the first shell. So selenium is 1s2. Now, again, why 2? Let's go back again to the periodic table. Because remember, up here, this is the S subshell. So all of these in here are the S. So hydrogen and helium. Helium really for electron configuration should be over here right next to hydrogen. So that would be 1s and then 1, 2. And then we come down here to lithium and beryllium. That's the second shell now. So that's 2s. So hydrogen would be 1s1. Helium would be 1s2. And then lithium would be 1s2, because we have to fill this one first according to the Aufbau principle. And then 2s1. Beryllium would be 1s2, 2s2. Boron would be 1s2. Again, always start at the beginning. 1s2, 2s2. And now these are the p subshells over here. So this would be 2p1. Carbon would be 2p2. Nitrogen 2p3, 2p4, 2p5, and then 2p6 is your maximum there. Okay, so remember selenium is number 34, way down here. So 1s2, 2s2, 2p6, 3s2, 3p6 takes us to argon right here. So now we're at 3. This is the third period. So this is 3s2. Over here is 3p6. And then we have to come down here and go to 4s. So we're going to go 4s2. Gets us to calcium now. Okay, and the only tricky part here is to know that when you get to this section here, this from number 21 to 30, you're in the D subshell. Okay, and the D subshell, this is one thing that students mess up, is always one behind the S's and the P's. So this is 3S, this is 3P over here. This is 4S, this one here is 3D. That's one of the tricky parts that you have to remember. Okay, so we go back here, we're going to go 3D10, gets us all the way over to zinc here. And now we're finally completed with that first D subshell. So this is 3D, this one is 4D, this one is 5D. It's always whatever the S one is, it's always one behind it. Now this was 3S, this is 3P. So if this is 4S, this one over here has to be 4P. And we've got to get to selenium. So we're going to go 4P1, 2, 3, 4 to get to selenium. So 4P4 is selenium. Okay, silicon. Again, got to find it on the periodic table. Silicon is right here, number 14. Okay, so let's go 1s2, 2s2, 2p6, 3s2, 3p. Now be careful here. 3p is right here, but we just need to go to silicon. So we just need 1, 2 there from silicon. So 3p2. Now notice that silicon has 14 electrons, and if you add up these numbers here up in the corner, if you've done it right, it better add up to the number of electrons it has. 2 plus 2 plus 6 plus 2 plus 2 equals 14. Same thing with selenium up here. Selenium has 34 electrons. Add up those numbers up in the corner. What do you get? You get 34 electrons. Okay, let's keep going here with silver. Silver is right here, number 47. Okay, and so we're going to, it's going to look really similar to silicon, but we're just going to keep going. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2 gets us to strontium. We're right here now, and now we need to get to silver. So remember, this is 3D, so the next row down is 4D. So we're at 4D, and to get all the way over there, we've got to be at number 9. So 5s2, 4d9. Okay, calcium a little bit easier here. I think we actually did one that actually this silver has calcium in it. And that's the nice thing is once you get this, it's the same thing over and over. So calcium is number 20. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 adds up to 20 electrons. Again, this part isn't part of the electron configuration. It's just making sure, do my numbers add up to the number of electrons in that atom? Okay, and then our final one is iron. Iron is right here, number 26. So it's actually just like calcium, but then again, you've got to go back into that D subshell to complete it. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and then we just count 1, 2, 3, 4, 5, 6. So 3d6 is the final electron configuration for iron. Now, I know I went through that pretty quickly. If you're still struggling with that, go on YouTube, type in electron configuration, watch some other videos of people doing the same thing. Okay? Now, you'll notice that when we did this, a lot of these, the beginning parts, all pretty much the same. And a lot of times we don't care about all of the electrons. A lot of times the only electrons we care about are the electrons that are in the very last shell. Now here's where we have to be careful. Because look at iron. Well, iron, well, what's the last shell? Well, I don't know, whatever the last one is. Well, technically, no, that's the third shell. That goes back here. The last shell of iron is actually the fourth shell. So the last shell is the one that has the greatest period number, or the one that has that number that is the greatest. So like on silver back up here, what's the last shell is actually the fifth shell electrons. Okay, and that last shell of electrons, the one that's the farthest away from the nucleus, the one that's going to interact with other electrons when another atom hits it, are what are called the valence electrons. Okay, so the valence electrons are the very last electrons, the one that are the farthest away from the nucleus. So a lot of times what we do is we say, hey, you know what? Forget all those inner shell electrons. Let's just focus on that last shell, the valence shell of electrons. So many times on the AP test, you might ask to be written. You might ask to write the electron configuration, but only showing the valence electrons. Or they'll say write the valence shell electron configuration. The same thing. For example, if they asked you to write the valence shell electron configuration for element number 88, Ra, which is way, way, way down here, you're like, oh my gosh, that's going to take forever. But if they say only show the valence electrons, it means only show the electrons that are in the very last shell. Well, if we count from the top, 1, 2, 3, 4, 5, 6, 7, Ra is in the seventh shell. And so the only thing we would have to write there is just that seventh shell, and it's in the S subshell. So all you would have to write is 7s2, and that's it. Now, I will tell you this. If they say write the valence shell electron configuration for Ra, and you write the whole thing, and the whole thing is perfect, they will still give you credit for it. But again, why? Okay? If you're asked to write the electron configuration for iodine, again, only showing the valence electrons, iodine should end in 5s2, 4d10, 5p5. But if they say only show the valence electrons, remember, it's whatever in the very last shell. That's the fifth shell. These electrons are back in the fourth shell. So what would you write? You'd just write 5s2, 5p5, because again, those 4d electrons are in the fourth shell, not the fifth shell. Remember that the valence shell is the final. It's the one that has the biggest number in the front. And it might just be like on calcium, it's just those electrons right there, because that's the only one that starts with a 4. Okay? But for example, on silicon, there's the third shell, but there's also the third shell. Those are all part of the valence shell. Okay, with selenium, again, it's these electrons here and these electrons here. You would say that selenium has 2 + 4, 6 valence electrons. Silicon has 2 + 2, 4 valence electrons. So whichever electrons are in the very last shell, it might be just the s subshell, it might be the s and the p subshell, okay, but whatever's in the very last one, those are the valence electrons. So for strontium, again, we've got to go back to our periodic table here. Strontium is in the 1, 2, 3, 4, the 5th shell, and it has 2 electrons in that s subshell, so we just write 5s2. Okay, for oxygen, we come back up here. Oxygen is in the 2nd shell, so that's 2s and 2p, and we've got to fill up that s subshell, so 2s2 and then 2p4. So oxygen has 6 valence electrons, strontium only has 2. Okay, for iodine, I believe we already saw that example of iodine. Was that iodine? Yeah, for iodine, it would just be what we saw before, 5s2, 5p5. For lead, lead is a little bit trickier here. Let's just take a look at it. So lead is way down here, number 82. Again, the last shell this is going to be 6s right here, and then you go down to the f subshells, and then you come back up to the d subshells. But just like the d subshells, the f subshells are also behind the s's and the p's. So whenever you're talking about the last shell, if it's an element over here on the left-hand side, it's just that s subshell. If it's an element over here, it's going to be the s and the p subshell, both of them. So for lead, again, we're not worried about the D subshell. We're not worried about the F subshell. Just that last S subshell and the last P subshell. So that would be 6s2, 6s2, 6p2. Okay, and then our last one, fictional element 119. Why am I putting that on there? Because it was on the AP test. That's why. And some students looked at this, wait a minute, there's no element 119. It only goes to 118. You're right, and that's why it said fictional element 119. If there were an element 119, where would it go? Well, I don't know, after 86, where's 87? Right here. After 118, where would 119 be? It'd be right down here, right below francium. Okay, and so that would be, if this is the 7th shell, then this one here would be the 8th shell. And there would just be one electron there, so it would just be 8s1. Okay? And so you can write electron configurations starting using the Aufbau principle, starting at the very beginning, 1s2, 2s2, 2p6, 3s2, 3p6, etc. Or you can also write electron configurations using just the last shell, what we refer to as the valence shell electrons.